3.5 is rational functions, graphs, applications, and models. We're really only going to be doing the graphs part out of section 3.5, and that in itself is a pretty hefty task. So I'm going to go over some of the concepts in general first. Then we'll do several examples showing some of the features that may show up in your graphs, and you'll want to get a lot of practice on this, graphing these on paper, not just working them on the computer. It's a completely different experience. So first off, let's look and take a look at what they look like when they're graphed. Here is a rational function, and I want to look at the graph. If we zoom out, we've got this type of behavior going on. If we go ahead and factor this, you might see some of the features that are showing up. So this is an x plus 2, x minus 2 on top for that factoring. All right. And you can see with this function, if you used a 5 or a 1 for x, that would make your function undefined. And if you look at your 5, right here is your 5, okay, or your 1 right there. Those are two places where you will not have any graph crossing those areas. In fact, it gets really close to them, but it never touches them. And the x-intercepts are here at negative 2, 0 and a 2, 0. And you can see that comes from your numerator here. Let's try another one. Here's another. You zoom out. It's a little bit different. Okay. And this one has a undefined value of x equals 1/2, and you can see there that that's this vertical line that the graph is getting close to but not touching, because if it touched it, it would mean that it has an x value of 1/2. Can't happen because it makes it undefined. All right, the definition of a rational function is where you have one polynomial over another polynomial, and we have to make sure that the denominator, q of x, does not equal 0, so that this stays as a defined function. A vertical asymptote, that's that feature we saw where you have some kind of value that's making your denominator 0, and it's a vertical line that the graph tends to. So when you have some kind of a graph that's going on, let's say that x equals 2 is your vertical asymptote. These are generally drawn as dashed lines. If your graph were going something like this, it would have this type of behavior, or it may have this type of behavior, but it gets infinitely close to it, does not actually touch the value of x equals k. It can come from this side as well, come from this side. You have all kinds of things that could happen. Now a horizontal asymptote is a line y equals b, because that's the equation of a horizontal line, where if your graph is approaching, your y is approaching b, as x either gets closer to positive infinity or negative infinity. So we have this dashed line. It doesn't really matter what's happening in here, but as we go out to positive infinity, maybe it's getting close that way, and as x goes to negative infinity, then your y is getting close that way. In fact, your graph out here, if you would just zoom in and look at that, it actually looks like enough like that line y equals b. Let's go ahead and get into graphing these. Let this be your strategy for graphing any rational function that you see. Anything that's in your homework, whatever strategy they ask you to use or whatever information they ask you for, just use this strategy in place of what they have. It's a full general strategy that you can use for all of these. Our first task is to factor the numerator and the denominator. Well, the denominator doesn't have to be factored, so there it is. You don't even have to put parentheses around it if you don't want. Your vertical asymptote is that value of x that causes the denominator to be 0, so x equals 1. And we can go ahead and graph that. X equals 1, it's that vertical line of x equals 1. An x-intercept, remember how you find x-intercepts is to make the y 0. So we can come over here, 0 equals 2x minus 4 over x minus 1. The way we would solve that is to multiply both sides by x minus 1. So when the left side is multiplied by x minus 1, we get 0. When the right side is multiplied by x minus 1, the x minus 1's cancel and we get 2x minus 4. So we end up with an x equals 2. So I know that my x-intercept is not x equals 2. This is the result of our process of solving for the x value, but we know that we got a 2 when our y was 0. You need to record those x-intercepts as a point. Now on finding the y-intercept, remember that you find y-intercepts by making the x's 0. So up here, if this x is 0, this whole term goes away. If this x is 0, that whole term goes away. So we're left with negative 4 divided by negative 1, which is 4. So we write 0, 4. And that further emphasizes the fact that when x was made to be 0, y equaled 4. Don't write just down the number 4. 4 is just a number. Don't write down y equals 4 because that's the equation of a horizontal line. Actually write it as a point. Now your horizontal asymptote, you can find it several different ways. One of the easiest ways to do it is to see that you have the same degree there on top and bottom. So then you just divide the coefficients. So 2 divided by 1 is 2. So your horizontal asymptote is the line y equals 2. Now we want to know, does it cross the horizontal asymptote? Students get real confused about this. Don't make it any more difficult than it is. It's not that hard. It's like if we had a t-table and we made the y2 and we tried to figure out what the x is that goes with it. If you find an x to go with it, then that's the crossing point. If you don't find an x to go with it, then it doesn't cross. So we're going to come up here and look at our function we have. We're going to make the y 2. So here's my work on that. 2 equals 2x minus 4 over x minus 1. I multiply both sides by x minus 1 so that I can get rid of the fractions. And I subtract 2x from both sides, I get negative 2 equals negative 4. And that is a not true statement. So anytime you're trying to find something in math and you get a nonsense statement, then that means you don't have what it is that you were looking for. In other words, you don't have a crossing point for your horizontal asymptote. When y is 2, you did not find an x. If you would have found an x, it would have ended up in saying something like x equals a negative 1/2. So then you would say it crosses at negative 1/2 too. That's all there is to that. A sign chart is really only needed if you graph all of these features and you can't figure out what the graph looks like from that. So let's see what we have to work with. I have my x equals 1 vertical asymptote drawn in. I have an x-intercept of 2, 0. I have a y-intercept of 0, 4. I have a horizontal asymptote of y equals 2. And we want to try and draw the graph from this. We have one vertical asymptote. That means we're going to have two pieces to our graph. And that vertical asymptote separates your graph into pieces. So one separation means two pieces. And it means I'm going to have either a graph up like this or a graph like this. And based on having a y-intercept right there, looks like I'm going to have the graph up like this. Remember, your ends get pulled toward the asymptotes. Remember the definition of asymptote up there. And on the right side of the vertical asymptote, I have a graph either here or here. And because of this point being right here, I know my graph is going to be sitting below the horizontal asymptote. And that is it. That's that graph. So we were able to figure that out without using a sign chart. If you wanted to use a sign chart just to double check, you can definitely do that. You list all of your factors that show up in the problem. You list the critical values that you get from that, and that would be 1 and 2, and test on all three parts, all three intervals. So I have 0, 2 is positive, 0 minus 2 is negative, 0 minus 1 is negative. Multiply all those together and it's positive. If I had 1.5, 2 is just a number that's positive. 1.5 minus 2 is negative, 1.5 minus 1 is positive, so this interval is negative. And over here, maybe a 3. 2 is a number that's positive. 3 minus 2 is positive. 3 minus 1 is positive. We multiply those all together and it is positive. So what does this mean? It means this interval from negative infinity until 1 on the x-axis is always above the x-axis. It's always above, always positive. And then from 1 to 2, it says from 1 to 2 we are below the x-axis, and most definitely we are. And after 2 we're always positive. There we go. After 2 we're always above the x-axis. That's how sign charts correspond with those rational functions. So it's kind of fun that you already know that. You don't have to learn something new for that. Alright, this next one, we've got a bit of factoring to do first. We're going to get it into factored form. So let's say we've got a 2x and an x and a 3 and a 3, a plus and a plus. And the denominator, a 2x and an x, a 2 and a 1, plus and plus, and that gives me everything I need. Vertical asymptote, remember, comes from the denominator, whatever makes it undefined. So an x equals a negative half and an x equals negative 2 is going to make this function undefined. So I have two vertical asymptotes on this one, and you go ahead and graph that if you want. one doesn't look quite so vertical. I'm going to redraw that. Okay. So since we have two vertical asymptotes, we're going to have three parts to our graph. The x-intercept, if we set this equal to 0 and solve, we will be able to find our x-intercepts. Remember, to find an x-intercept, you make the y equal 0. When I multiply both sides by the denominator to clear the fractions, I end up with just the numerator. And when I would go ahead and solve that, I get a -3/2 would cause my y to be 0, and a -3 causes my y to be 0 there. So I have -1.5, 0, and a -3, 0. For y-intercept, remember we're making the x's 0, so these terms completely go away. I just have 9/2 left on that. So when x is 0, y is 9/2. Horizontal asymptote. We have same degrees here, x squared and x squared. So we divide the coefficients. 2 divided by 2 is 1. So y equals 1 is our is our horizontal asymptote. Draw that in. 1, 2, 3, 4, 5. And this is our y-intercept there. And we want to know, does it cross the horizontal asymptote? If we make y equal 1, then we would end up with 1 equals 2x squared plus 9x plus 9 over 2x squared plus 5x plus 2. Now I'm using the unfactored form here for the ease of it. As you do a few of these, you'll realize which form, either factored form or expanded form, is going to be easier for what you're trying to find. You'll get a good feel for that. So multiply both sides by the denominator to clear the fractions. I get 2x squared plus 5x plus 2 on the left, and on the right the denominator goes away. I get this. Subtract the 2x squared from both sides, so I have 5x plus 2 equals 9x plus 9. And I'm going to subtract the 5x from both sides. That gives me a 4x. And subtract 9 from both sides. That gives me a -7. So divide both sides by 4. And I get an x value of -7/4. So yes, it crosses. We got an x value. Not only do you have to say yes, but you have to tell me the point where it crossed. And think about this. You let the y equal 1 and you got a -7/4 for the x that goes with that y value. So that is your point. Let's go ahead and draw that. -7/4, 1. So we're crossing the horizontal axis or horizontal asymptote at that point. Okay, let's see if we can get this graphed without having to do a sign chart. I know I have a graph either here or here, and it's obvious because I have this point here that I have to have on my graph that we have a graph that's doing this kind of thing. Okay, let's connect these points right here. And this one, the graph gets drawn towards the asymptote. And this one here, the graph gets drawn towards the asymptote like so. And then here, the graph gets pulled towards that asymptote, picks up this point on its way to getting pulled towards that horizontal asymptote. And we were able to graph that fine without doing a sign chart. If you want to be sure, you can always draw a sign chart and double check what the graph behavior is above and below the x-axis between those intervals, in those intervals. For this next problem, we'll want to go ahead and factor the numerator. And the denominator doesn't need to be changed at all. Our vertical asymptote, because of the denominator, is going to be x equals a negative 1/2. And the x-intercept, by setting the y equal to 0, we will get two x-intercepts of 4, 0, and negative 1, 0. Your y-intercept, it's easier to look at the unfactored form, so make the x's 0 and the y will be negative 4, so we have a 0, negative 4 there. And horizontal asymptote, these are not of the same degree, so we have to put in a missing term here of 0x squared and then divide the coefficient. So 1 divided by 0 is undefined, and that means that we do not have a horizontal asymptote. So we're not going to answer the question about crossing the horizontal asymptote either. What we will have is a slant asymptote. Some texts call them an oblique asymptote. And so this would be a line that's diagonal. And to figure out its equation, we actually take the numerator and divide it by the denominator using polynomial division. Now, if you have a divisor that is a plain x plus or minus some number, then you can use synthetic division, but this has a 2 in front, so we have to use just regular old polynomial long division, and do that right now, where we divide up. X squared divided by 2x is 1/2 x. 1/2 x times 2x plus 1 is x squared plus 1/2 x. And remember that we draw our line, change our signs, and combine down. So x squared minus x squared is gone. I have a negative 3x minus 1/2 is negative 7/2 x. Carry down the minus 4. And then we do the cycle again. Negative 7/2 x divided by 2x is a negative 7/4. And you can actually stop right there. That tells you what your slant asymptote is. It's the equation y equals 1/2 x minus 7/4. Now what we'll do is go ahead and graph what we have to see if we can figure out what our graph does instead of trying a sign chart. If we need the sign chart, we can do it. But remember, it's just a tool to help you in case you can't quite see what's going on by the other information. Putting my vertical asymptote in here, and I have x-intercepts of 4, 0 and negative 1, 0. We have a 0, negative 4 down here for y-intercept. And the slant asymptote, it has a y-intercept. I'm going to do this in a different color. It has a y-intercept of negative 7/4, so negative 1 3/4. Now you have to remember this is the y-intercept for the asymptote, not for the actual graph. It's the y-intercept for the asymptote, and the slope is to go up 1 and right 2, up 1 and right 2. So we are not going through that x-intercept that's over here. Okay. And let's see if we can get the graph drawn. We'll either have a graph this way or this way. And since we have a point there to go through, we have to draw the graph like so. And we have another point here and a point here. Remember that this asymptote continues this way. So we're going to go like this, and the other end gets drawn towards the asymptote and going through that other point as you go. And that's what these graphs look like. If the numerator degree is higher than the denominator degree, you end up with that slant asymptote. All right, we have another where we are going to factor. And you notice here we have a common factor on top and bottom, so this can be simplified to be x plus 1 over x minus 3. And we'll come back to this in a little bit, but it's a good thing to note when you have a common factor on top and bottom, this means that you're going to end up with a whole at that x value of 1 and some y value. So we'll come back and figure that out. Vertical asymptote, you just want to focus on this here for the rest of the information. Vertical asymptote is x equals 3. X-intercept is -1, 0. The y-intercept is 0, -3. Sorry. The y-intercept is 0, -1/3. The horizontal asymptote is y equals 1, and we need to see if it crosses the horizontal asymptote. It does not. Put the 1 right there and get x plus 1 over x minus 3. When you multiply both sides by x minus 3, we get x minus 3 equals x plus 1. When you subtract x from both sides, you get -3 equals +1. It's a false numerical statement, so no, it does not cross the horizontal asymptote. Remember, if it does, then you need to say that it does, but also write what the point is where it crosses. We'll hold off on the sign chart. We may not need it. So we have 1, 2, 3, x equals 3 for our vertical asymptote. We have a -1, 0. We have a 0, -1/3. We have a y equals 1. And no crossing point for that. So I know that I have a graph that's doing this and a graph that's doing that. But let's go back up to this whole that we have. If I had a 1 in the x part here, I would have a 1 plus 1 over 1 minus 3, which is 2 over -2, which is -1. Means I have a whole at 1, -1. So draw yourself an open circle there so you know you have that point of discontinuity in your graph. And this graph will pick up those points and go this way, and connect, go this way, but make it clear that you've got a you've got an open spot right there. In the other piece, we have a graph either here or here. When knowing that the ends get pulled toward the asymptotes, if our graph was down here, we would have a crossing point right there. We do not have another x-intercept. So we know that the graph has to be here. Sometimes you don't know what your graph is going to be based on the information that you found, but you know what it is based on what you don't have. Since we don't have another x-intercept here for us to go through and get pulled toward that asymptote, we know that it must be up here. Again, we didn't have to do a sign chart on this one, so I just skip that step. Okay, let's see what we have here. We have an x minus 2, and an x plus 3 quantity squared. Vertical asymptote is x equals -3. X-intercept is 0, 0, and 2, 0. Y-intercept is 0, 0. Horizontal asymptote, we have same degree on top and bottom, so we compare, divide the coefficients. 1 divided by 1 is 1. So y equals 1 is your horizontal asymptote. How to see if we cross is we make the y equal 1 and see if we can get an x value that goes with that. I'm going to multiply both sides by x squared plus 6x plus 9. The left side becomes x squared plus 6x plus 9, and the right side, the denominators cancel, so I end up with 6x plus 9 equals a -2x. That means a -8x is 9, so x is a -9/8. So I'm crossing yes, and I'm crossing at -9/8 for the x when the y is 1. All right, x equals -3 is the vertical asymptote. X-intercept 0, 0, and 2, 0, and y-intercept 0, 0, of course. Y equals 1 is your horizontal asymptote, and we cross at -1 1/8, 1. So I'm going to draw that point there, and we'll see what's going on here. I know my graph has to do something like this over here, because if it were down here, we'd have to have another x-intercept over here for it to cross through, and it does not. So I'm going to go like this, pick up this point, and the end gets pulled toward the asymptote. All right, now if you want some good practice, these are some excellent problems to just graph out of your book. Look on page 377 where they start, and those are excellent examples that you can get more practice on besides what you do in MyLabs Plus. You should be ready to go ahead and try your homework, and good luck. Let me know if you have any questions.